Hello everyone. In this class, I'm going to discuss about the CMOS inverter and CMOS realization of logic gates. So these topics are in Unit 4 of the subject Integrated Circuits. Contents are CMOS inverter, NAND gate and NOR gate using CMOS. Once we understand the CMOS realization of NAND gate and NOR gate, we can easily implement the CMOS circuits of other logic gates also, like XOR gate, XNOR gate, etc. So starting with the CMOS inverter, firstly I will discuss the basics of the CMOS inverter, and after that I will come to the CMOS realization. So CMOS, it stands for complementary, C for complementary, MOS means metal oxide semiconductor. So CMOS stands for complementary metal oxide semiconductor. Like you had studied about the transistor. Transistors are classified into two parts. One is BJT, another one is FET. The further FET has been classified into two parts, JFET and MOSFET, but normally we use MOSFET. So MOSFET is of two types. One is NMOS and another one is PMOS. That works in two modes, enhancement mode and depletion mode. Fine. So NMOS and PMOS, there are two transistors. NMOS, that is N-channel MOSFET. PMOS, that is P-channel MOSFET. So to construct CMOS, what we do, we take one PMOS transistor and one NMOS transistor, and both are vertically aligned. Fine. For example, this is the symbol of PMOS. You can see in PMOS, the source, the arrow is inverts, right? And the terminal at which this arrow is there, that is called source terminal. And this is PMOS transistor. And in NMOS, the arrow is outward direction. This is NMOS. Now, to construct the CMOS inverter, the drain of PMOS and NMOS are shorted and the gate are shorted, and we apply the input Vin at the gate of the NMOS and PMOS. As we know that the source of the PMOS terminal is at higher potential, that is VDD, and the source of the NMOS is at lower potential, that is ground. And we take the output of the CMOS inverter from the drain terminal of NMOS and PMOS. So this is Vout. So this is the CMOS inverter, which consists of two transistors, NMOS and PMOS. The source of the PMOS is connected to VDD. The source of the NMOS is connected to ground. We apply the input signal at the gate terminal of the NMOS and PMOS. This is one is the gate terminal. And we take the output of the CMOS inverter from the drain terminal of the NMOS and PMOS. Now, the question arises that why this CMOS structure is called inverter? Why it is called inverter? Inverter, we know that is at NOT gate. It means that when we apply logic 0 at the input, we will get the logic 1 and vice versa. So to understand the working of this CMOS inverter, firstly, take the case first. Case first is when Vin is high. When Vin is high. When Vin is high, then you can see that NMOS will be on and PMOS will be off, because NMOS transistors becomes on at logic 1 at the gate and PMOS becomes on at logic 0 at the gate. So if NMOS is on and PMOS is off, PMOS is off, NMOS is on, it means that the Vout, it will be connected to ground. So output will be at lower potential. So output will be low. It means that when Vin is high, then in this case, Vout is low. Similarly, another case is when Vin is low. When Vin is low. Now when Vin is low, that means the voltage at the gate terminal is low. In this case, PMOS transistor will be on while NMOS will be off. Now PMOS is on, NMOS is off. So this Vout, output terminal, it will be connected to supply voltage VDD. Means output will go to the higher voltage side. It means that output will be high. It means that Vout will be high. Now you can see that when we have applied input high, then we are getting output low. And when we are applying input low, then we are getting output high. So it is acting as a NOT gate. That's why this structure is called inverter. Although we can design the inverter using NMOS also, PMOS also, BJT also, but there are various advantages of CMOS, and the one advantage is the steady state power dissipation of CMOS inverter is very less. That is one advantage. Another advantage of CMOS inverter is its noise margin is very high. Its VTC is very sharp. VTC, that is called voltage transfer characteristics, right? The VTC of CMOS, it tends towards the ideal characteristics. Fine. So these are some advantages of CMOS inverter, but the biggest advantage of CMOS inverter is that its steady state power dissipation, it is very less. It is very low. As far as limitations of CMOS inverter is concerned, there is one problem in CMOS inverter that is called latch-up problem. Latch-up problem occurs because internally while fabrication of CMOS inverter, since there are NMOS and PMOS both transistors and there is only one substrate, P substrate. So in that case, parasitic bipolar transistors are formed, due to which the current sharply increases. So to avoid this problem, we use additional guard rings in the CMOS inverter to avoid the latch-up problem. So there is a problem called latch-up problem, but we have the solution. That solution is the additional guard rings. And another limitation of CMOS inverter is that the fabrication process is a little bit complex in comparison with other technology. But since it has many advantages, that's why that disadvantage, that limitation can be ignored. Right? So this is all about the advantages and limitations of CMOS inverter. Now we are very much interested in the CMOS realization of various digital circuits. For example, logic gates, adder, subtractor, multiplexers, decoder, encoders, flip-flops, master-slave flip-flops. Fine. So we are interested in the CMOS realization. The reason is very clear, that is the power consumption is very less. So we need to understand that how we can realize different digital circuits with the help of CMOS. And the very basic is the CMOS realization of the logic gate. So we need to understand how we draw the CMOS circuit of different logic gates. So to understand that topic, firstly, let us complete the basics for that. For example, see, when we design any digital circuit with the help of CMOS circuit, it means that we are using NMOS transistors and PMOS transistors, and we had seen the circuit, transistor level circuit of CMOS inverter, which consists of one NMOS and one PMOS transistor, and the input is same at both the transistor, at the gate of both the transistor. It means that if we want to design two input logic gate, fine. So it means that we will be requiring two NMOS transistors and two PMOS transistors. Similarly, if we want to implement any Boolean expressions which consist of 4 variables, so 4 inputs are there, so we will be requiring 4 NMOS transistors and 4 PMOS transistors. So these NMOS and PMOS transistors, it can be in series, it can be in parallel. So when we connect NMOS transistors in series, when we connect NMOS transistors in parallel, similarly when will we connect PMOS transistors in series and parallel, how we decide that? For that, we need to understand it. For example, if two NMOS transistors are in series, let's say these transistors are M1 and M2, and the inputs are M1 and M2 are A and B. See, this is the pull-down network, right? And the upper one is the pull-up network. That pull-up network, it consists of PMOS transistors. It consists of PMOS transistors. And the pull down networks, it consists of NMOS transistors. Fine. Now see, there can be 4 cases. Fine. The case 1 is when 2 NMOS transistors will be in series. Case 2 is when 2 NMOS transistors will be in parallel. Similarly, case 3 is when 2 PMOS transistors will be in series, and the case 4 is when 2 PMOS transistors are in parallel. So starting with the case 1, when 2 NMOS transistors are in series. Now you can see that from the pull up and pull down network, we take the output Y. Now see, output Y will be connected to ground only when M1 and M2 transistors are on. It means that Y will be equal to when A and B both are on, and not A and B, M1 and M2 transistors are on, but M1 and M2 will be on when A and B will be high, because M1 and M2 are NMOS transistors, and NMOS will be on at logic 1. And output, only then output Y will be connected to ground. It means that Y bar, since it will be connected to ground. So from here we can write Y is equal to A dot B bar. It means that when there is a dot operation with inversion, then NMOS transistors will be in series. Similarly, case 2 is when 2 NMOS transistors are in parallel. When 2 NMOS transistors are in parallel. So the source of the NMOS transistors are connected to ground. Let's say these transistors are M1 and M2, and at the gate of M1 we have applied input A, at the gate of M2 we have applied input B, and this is the output Y. See, I have only drawn the pull down network, and the upper network is pull up network. That will be case 3 and case 4. Now see, output Y will be connected to ground if M1 transistor or M2 transistor will be on. If one of them is on, in that case also Y will be connected to ground, or if both are on, even then Y will be connected to ground. So it means that the expression of Y, it will be equal to A plus B, since either M1 or M2 will be on, and it will be Y bar, since Y will be connected to ground. So Y will be equal to A plus B whole bar. It means that when there is a OR operation with inversion, then 2 NMOS transistors will be in parallel. Similarly, coming to case 3. Case 3 is when 2 PMOS transistors are in series. 2 PMOS transistors are in series. So, and these PMOS transistors are, let's say these are M3 and M4 transistor. This is the supply voltage VDD, and at the gate of the M3 and M4 we have applied A and B, and this is output Y. And the lower network, it will be pull down network, that I have discussed in case 1 and case 2. Now see, output Y will be connected to VDD only when both the transistors M3 and M4 are on. And since M3 and M4 are PMOS transistors, so to make sure that M3 and M4 are on, for that A and B should be 0, because PMOS transistors become on at logic 0. So Y will be equal to A bar dot B bar. Since both the transistors should be on, that's why there is a dot operation, and I have written A bar B bar. Reason is that A and B should be low in order to turn on the PMOS transistor. Since Y is connected to VDD higher side, that's why I have written Y, not Y bar. In NMOS case, I have written Y bar, since in that case Y is connected to ground. Now from here we can apply the De Morgan's theorem, and it can be written as A plus B whole bar. So A plus B whole bar, it can be written as A bar dot B bar. So it means that when there is a OR operation with inversion, so PMOS transistor will be in series. It will be in series. But in case of NMOS transistors, we had seen that when NMOS transistors are, when there is a dot product, in that case NMOS transistors are in series. But in PMOS, if there is a OR operation, then PMOS transistor will be in series. Fine. Last case is case 4, when 2 PMOS transistors are connected in parallel. This is output Y, and the lower network is pull down network that consists of NMOS transistors. These are the transistors M3 and M4. Since these are the PMOS transistors, so source of these PMOS transistors will be connected to supply voltage V. Let's say A is applied at the gate of M3 and B is applied at the gate of M4. Now Y will be connected to supply voltage VDD only when either M3 is on or M4 is on or both are on, right? So Y will be equal to A bar plus B bar. So it can be further written as A dot B whole bar. So A dot B whole bar is equal to A bar plus B bar as per De Morgan's theorem. Fine. Now see, it means that when there is a dot operation with the inversion, then PMOS transistors will be in parallel. So these are the 4 cases to understand that when the NMOS and PMOS transistors will be in series and parallel. So we can summarize it. In summary, we can say that when there is a dot product, with inversion, then in that case, NMOS will be in series and PMOS will be in parallel. Similarly, when there is a OR operation, it's the XOR operation. In fact, when there is a OR operation, that is plus OR operation, in this case, but OR operation with inversion, because there is a bar, right? NMOS will be in parallel and PMOS will be in series. Fine. Now, by considering these things, now we are going to design the CMOS circuit of NAND gate and NOR gate. Now, one more thing is there. You had seen that when the NMOS transistors are in series and then PMOS are in parallel. When NMOS are in parallel, then PMOS are in series, right? That's why pull-up and pull-down networks are called dual networks. Pull-up network means pull-up network which consists of PMOS transistors. Pull-down networks which consist of NMOS transistors. And we have seen that when NMOS transistors are in series, then PMOS are in parallel. When NMOS are in parallel, then PMOS are in series. That's why pull-up and pull-down networks are called dual network. Now, by considering these things, we are going to implement the CMOS circuit of NAND gate and NOR gate, starting with the CMOS implementation of NAND gate. CMOS implementation of NAND gate. So, we know that for NAND gate, 2-input NAND gate, we are considering 2-input NAND gate, the expression Y is equal to A dot B whole bar. A dot B whole bar. Now, you can see that there is a dot product with inversion. It means that NMOS will be in series, and if NMOS transistors are in series, then PMOS will be in parallel. So, how many transistors will be required to draw the CMOS circuit of NAND gate? So, it depends upon the number of inputs. And I have taken 2-input NAND gate. It means there are 2 inputs. So, we will be requiring 2 NMOS transistors and 2 PMOS transistors. Total 4 transistors. And these 2 NMOS transistors will be connected in series because there is a dot product with inversion, right? And if NMOS transistors are in series, it means that PMOS will be in parallel. So, considering 2 transistors M1 and M2, in series, and the inputs of M1 and M2 are A and B. So, this is the pull-down network which consists of NMOS transistors M1 and M2. Now, corresponding to it, we can draw the pull-up network which will consist of PMOS transistors. Since NMOS are in series, so PMOS will be in parallel. And the source of the PMOS will be connected to higher potential, that is VDD. Let's say these transistors are M3 and M4, and we know that in CMOS inverter the same input is applied to NMOS and PMOS both. So it means that inputs of M3 and M4, it will also be A and B, and pull up and pull down network will be connected, and from the drain terminal we will take the output, and this output Y will be A dot B whole bar. So we have designed this CMOS circuit of NAND gate using 4 transistors, M1, M2, M3, M4. M1, M2 are NMOS transistors, M3, M4 are PMOS transistors. Now we need to verify the truth table of this CMOS circuit. So in digital, you have studied the truth table of NAND gate. So truth table of NAND gate, inputs are A and B, output is Y. Since inputs are A and B, so there will be 4 combinations, that is 0, 0, 0, 1, 1, 0, 1, 1. So when A and B both are 0, so output will be 1. And for the remaining cases, 0.1, that is 0, and inversion of 0, that is 1, 1, and 1.1, 1 and 1. NAND operation will result in 0. So this is the truth table of NAND gate. So we need to verify this truth table with the help of this transistor level diagram. So we will verify it case by case. So starting with case 1, once you understand one case, you can do other cases yourself. Case 1 is when A is equal to 0 and B is equal to 0. When A is equal to 0 and B is equal to 0, just write down that which transistors are on and which transistors are off. Now you can see that when A is 0 and B is 0, then M1 will be off and M2 will also be off, because M1 and M2 are the NMOS transistors and MOS becomes on at logic 0. But M3, M4 will be on. So it means that M1, M2 will be off, M3, M4 will be on. If M1, M2 are off, it means that it will be open circuit. So Y will be connected to VDD. It means that output Y, it will be high, right? That is the first case. Similarly, we can go for case 2 also. Case 2 is when A is equal to 0 and B is equal to 1. Now see, when A equal to 0 and B equal to 1, then which transistor will be on and which one will be off? M1 transistor, it will be off since it's an NMOS. M2 will be on. Of course, M2 will be on because at M2 the input is B and B is equal to 1. Similarly, what about M3 and M4? M3. At the gate of M3 there is logic 0. Since it's a PMOS transistor, so M3 will be on, but M4 will be off. Now you can see that in the pull down network, one transistor is on, one is off. So Y cannot be connected to 0 since M1 and M2 are in series. So Y is connected to VDD. It means that Y will be high. So we have verified the second case also. Similarly, you can verify third and fourth case also. Third case is when A equal to 1, B equal to 0, and the fourth case is when A and B both are high. Fine. So we need to verify the truth table of NAND gate with the help of CMOS circuit, transistor level circuit. So this is all about CMOS implementation of NAND gate. Similarly, we can implement NOR gate using CMOS. So next topic is CMOS implementation of NOR gate. CMOS implementation of NOR gate. So we know the symbol of NOR gate, and again considering the 2 input NOR gate, output is Y, and the truth table, we can make truth table for NOR gate. Inputs are A and B, output is Y. There are 4 cases, 0, 0, 0, 1, 1, 0, 1, 1. So for 0, 0, what will be the output? It will be 1. For 0, 1, what will be the output of the NOR gate? It will be 0. Right? Now, firstly, we need to draw the CMOS circuit of the NOR gate, and y is equal to A plus B whole bar. So it's a OR operation with inversion. It means that NMOS transistor will be in parallel and PMOS will be in series. So this y is equal to A plus B whole bar. Fine. So how many transistors we will require? Since there are two inputs, so corresponding to two inputs, we will require two NMOS transistors and two PMOS transistors. Fine. And NMOS transistors that form pull down network, NMOS transistors will be in parallel. So firstly, draw the pull down network. So considering two transistors M1 and M2 in parallel, and the inputs of M1 and M2 are A and B, and the source of these M1 and M2 transistors, and since these are NMOS transistors, it will be connected to ground. Since NMOS transistors are in parallel, so PMOS transistors will be in series. So considering two PMOS transistors in series, let's say these transistors are M3 and M4, and the source of PMOS transistor, it will be connected to supply voltage VDD. Since we are designing NOR gate using CMOS inverter, it means that the input will be same to the PMOS also. It means that the inputs of M3 and M4, it will be A and B, and from the drain terminal of this pull up pull down network, we will get output Y, and Y will be equal to A plus B whole bar. A plus B whole bar. So this is the CMOS implementation of NOR gate. So total 4 transistors are required: M1, M2, M3, M4. M1, M2 are NMOS transistors connected in parallel, M3, M4 are PMOS transistors connected in series. Now we can verify the truth table, that is called working of this circuit, and we will verify the truth table case by case, considering the case 1. Once you understand one case, you can easily verify the other cases also. Case 1 is when A equal to 0 and B equal to 0. Now see, when A equal to 0 and B equal to 0, it means that M1 will be off and M2 will also be off. So M1, M2 will be off. M1, M2 will be off. And what about M3, M4? M3, M4 will be on, since M3, M4 are PMOS transistors, and PMOS transistors become on at logic 0. So you can see that since pull down network, it is not active, this output Y, it will be connected to VDD, so output Y will be high, right? So this is the first case which we have seen. Similarly, we can verify case 2, case 3, case 4 easily. Just mention that which transistors are on and which transistors are off. So this is called the working of CMOS implementation of NOR gate, where we have verified the truth table of NOR gate. So in this class, we have implemented NAND gate and NOR gate using CMOS. We are interested in NAND and NOR gate because NAND and NOR are the universal gates, and with the help of universal gates, we can design other gates. Similarly, we can design XOR gate, XNOR gate, AND gate, OR gate. And as far as NOT gate is concerned, NOT gate is basically your CMOS inverter that I have discussed at the starting of this class. This one. So this is CMOS inverter. This is basically NOT gate. Fine. So by using these concepts, you can design the CMOS circuit of XOR gate, XNOR gate, NAND and NOR gate. Thank you.